On air. All right, it should be going, but I haven't tested the microphone yet, so. Refresh. I'm muted. Oh, Ryan is here.
Somewhat.
Hey, Ryan, can you hear me all right?
I can, actually.
From back here, too?
Yes.
All right. That's good enough for me, then.
Hey, is Travis there, by the way?
No. Is he planning on showing up?
No, I was just trying to catch him because he gave away his outdoor key.
Okay.
Alrighty.
All right. It's 6 o'clock. Hopefully no one shows up at 7. Sorry for that mistake. A lot of stuff here happens at 7, and I hadn't clicked when I made the flyer. But all right, so this is about 5 or 6 classes I'll be doing Thursday nights. Hopefully to get all of you started building your own robots or home automation or anything like that. It's going to be starting out tonight with the fun stuff I remember from physics, and I spent the last 4 weeks realizing how much I've forgotten from physics. So there might be some questions I can't quite answer or some fuzzy topics, but hopefully there's some stuff you didn't know and stuff you find interesting. Then next week we'll start circuits and just building your own circuits, basics learning first of all, and then some hands-on stuff afterwards. And right now I'm thinking of doing 2 classes on that. I have no idea how quickly these are going to go, so we'll see. After that, class on microcontrollers, just primarily the Arduino, but there are all sorts of different options out there. Just try to let you know how you can interface with them, what they can do, possibilities, stuff like that. And then the last part will be programming, to program those types of devices to be the brains of whatever you want to build. So, to get started, I'm going to do that all night. All right. So, I'll try and throw in some humor every once in a while, but. This is what I remember, and I think a lot of people remember from freshman physics, is the 4 fundamental forces are what control everything in the universe, and 2 of them are really easy to understand. The other 2 are kind of blah-de-blah, it's really hard to understand. But delving into it is kind of the opposite, because things like gravity, which is kind of easy to describe in the big sense, is actually the least understood of the fundamental forces. But to get started, I'm going to kind of delve down to the very basics of the standard model, which is what the guys at CERN are building and working on, trying. This is the most popular theory of what everything in the universe is made up of. And you have in the center your forces, and then the outside bosons, quarks, things like that. Quarks might sound familiar to you. They are what protons and neutrons are made up of inside of an atom. Other things, E right there, that's the electron, which here in the another model of the atom, you've got electrons orbiting the outside of an atom, and in the nucleus you have protons and neutrons. And well, in electricity, we're most interested in the electron, and then also the photon. Those are the photon being the force carrier for what causes a lot of the force behind electricity, essentially. And let's see. Might be a little bit too deep, but The electron, let's just start there as well, because as everyone, or the atom, this is kind of the, let's go to the next slide. You've got the Bohr model of the atom. Some of you might have heard of Niels Bohr. I like to tell everyone, you don't know my name, Niels, like the physicist, Niels Bohr. So the Bohr model of the atom, you've got protons and neutrons in the center. Protons are positively charged, neutrons have no charge, and then electrons are negatively charged, and in this model they orbit around the nucleus. And the electron is what we're interested in here in electricity. The electron has a couple properties. It has charge, so it's negatively charged. And it also has spin, which contributes to the magnetic force. So here out in the macro world, we are familiar with magnetics because magnets. Everyone can kind of see how they work. And magnets have north and south poles, and opposites attract. So the magnets pull together or retract depending on which side of the field you're on. Charge is very similar as well. Charge is like you have a balloon and you rub it against your shirt. What you're doing is transferring electrons from one material to the other, and thus there's an imbalance. So one has more electrons, which are negatively charged. So therefore it has a larger negative charge than the other, and they then attract and will stick. So both of those forces are caused by the electron, and both of them fundamentally are caused by an interaction, an exchange of of the photon force carrier between the particles, between electrons and protons.
Got a question.
Yep, go ahead.
So you're saying when you take the balloon and rub it on you, okay?
Yep.
What you're doing is you're transferring electrons that are made up of protons.
Well, no, electrons are just on the outside of the atom chart.
Okay.
Some materials are easier to give away electrons, and some it's easier for them to take electrons on.
Right.
And I'll kind of get to that in the next slide. And that's static electricity, electrostatic. Electrostatic force. Let's see here. So so the next slide I'm going to kind of talk about what makes some elements magnetic and some elements have electrical charge or electrostatic charge. Now, before I'll go ahead and keep going with this. As I put this class together, I was learning how much I didn't know. So this is kind of one popular theory and an easy way to explain it. I'll get into it more later, but so right over there we have, I believe it's a copper atom. So 29 protons and 29 electrons. All atoms will have the same number of electrons and protons, just kind of on their own. And this is the periodic table, and as you can see, as you go from top to bottom, left to right, they increase in the total number of protons and electrons. Now, copper is here, and copper and silver and gold, you can see, this is kind of from chemistry that I remember learning this. You'll see how many orbitals there are. So as you increase in the number of protons, you increase the number of electrons. And there are certain arrangements and orbitals, as they're called, that electrons will kind of stack up and build up out from the nucleus. And here in this one, you can see like there are 2 in the first one. If you look up here in the first row, there are just 2. Well, there's hydrogen and helium. And then the second row, you've got another 2 of this one type of orbital, and then another 6 of another type of orbital. So in this model, you've then got 8 in that second row. And in the third row, you have more. And then what's interesting about copper is that, so that fills up, and then you have just 1 on the outside. And so since it has just that 1 on the very outside, and copper, silver, and gold are all like that, you'll see here it lists 2, 8, 18, and 1. And this one has another 18 and then another 32. But they all have 1 in the very outside. And so that electron is not really held on that strongly. And it's easy for copper to then lose that electron, for the electron to move from one copper atom to another copper atom. And that is why those 3 elements are very good conductors. Now similarly, like hydrogen, lithium, sodium, potassium, they also all end with just 1 in their outer shell. They're also very good electrical conductors, but they're also highly reactive. So they're not very practical for electricity.
Gases too.
Yes, and gases. And then you have some other elements like tin and lead, aluminum, these transitional metals that when combined they form crystal structures which will, in how the crystals arranged, they'll also end up with kind of free electrons floating around in between the elements in the crystal structure. So that's why that's why some elements are electrically conductive. And go back a slide, because this is something I also just learned putting this class together. Somehow through all of college, I never learned what makes some materials magnetic and others not. And for some reason, I always thought it had to do with charge, but it does not. It has to do with electrons and how they spin. So if you have a whole bunch of electrons, here you can see they spinning left or right, they call it an up or down spin. If you have a whole bunch of electrons, well, naturally, in most elements, they're going to kind of, if you have one up, then you have another one down, spinning the opposite way so that everything evens out. But some elements will get more up than down, and thus, for the whole atom, you'll have a positive electric field in one direction, north to south, as we commonly say, through the atom. So that is something I learned putting this together.
I'll ask a question.
Sure.
When you were a kid, you'd say you could magnetize something, you used to rub something on a magnet, and then you could pick up other stuff.
Mm-hmm.
What's going on there?
Well, so first of all, it has to be a material that that is polarized itself, can be, like iron, I believe. And then you're rubbing it against a magnet. You're basically putting it inside a magnetic field, and the longer it's in there, and probably friction maybe helps as well, but you're basically aligning all the atoms in that molecule to line up with that magnetic field, so that when you then take it out of the magnetic field, they'll all be lined up and they'll have their own magnetic field.
Sure. Basically changing the way they go up or down.
Their orientation, right.
Okay. Thank you.
Yeah.
Take that even a step further. A few weeks ago, I discovered that some types of stainless steel can be magnetic, but others are not.
Yeah, there is very not.
That has to involve those.
Yeah, I'm not sure that.
Because we discovered that magnets don't stick to the front of our refrigerator.
Yeah, it's stainless steel. Yeah. Unfortunately, it is not magnetic. All right. So what is electricity? When you get down to it, you've got this, which is copper, which is a whole bunch of copper atoms with loose electrons kind of floating around in there that can easily move around. If you connect something that is electrically conductive to a battery is a source for, let me see, well, I don't really explain it. It's an electric potential. It's a difference in charge. So on a battery, on the negative terminal, you'll have more electrons, more negatively charged electrons on the negative half of the terminal of the battery. And the positive half of the battery, you've got a bunch of positive atoms, or atoms that are missing electrons and are therefore have more protons than electrons, and thus it's positively charged and wants to suck in extra electrons. So you've got the electrostatic force on this end. All these electrons together, they're all negatively charged and opposites repel, and so they're pushing each other apart. You connect that to some copper, and they're going to start pushing electrons down that copper wire. And as long as there's somewhere for them to go on the other end, they're going to just go all through the copper and end up on the other half of the battery. And in a nutshell, that's what electricity is. It's the flow of electrons. Now, conventionally, we say electricity flows from positive to negative, and that's what we call positive voltage. It's because Edison and those guys didn't really understand what was happening, and they just chose this half to be positive and that half to be negative. And when we figured out what was actually happening was actually a flow of electrons in the other way, that's when we said, well, electrons then are negative, so that if you have a negative flow going in one direction, mathematically that's the same thing as a positive flow in the other directions. So don't get confused later on about voltage and which way it's flowing. Conventionally, we say positive poles is actually kind of what they call them,
Yeah, I was just going to say the conventional theory is plus to minus,
right,
and hole theory or electron flow is negative to plus.
Yeah.
Now, question on.
Yeah.
The only thing I know about electricity is when I flip a light switch and when I pay the bill.
Yeah.
That's how much my physics are. So you're telling me that I got a car battery.
Yep.
I got a negative post and a positive post. I know you don't cross them.
Yeah.
So
if you want electricity, you do, but yeah,
Just through a load.
Yeah, through a load.
through a load, yeah, okay. So my question is, you got a car battery, right?
Yep.
Yeah, negative, positive.
That's a
How,
DC.
okay, well, how do the electrons to go hang out on the negative post?
Well, so in a battery, you have a chemical reaction occurring in there that keeps it at a state of imbalance, so that on the negative post you'll always have more electrons, on the positive post you'll always have more, positive charge until the chemical reaction is depleted itself. So that's what's happening in a battery. Capacitors, on the other hand, are purely just electrons gathering up on either side of a capacitor. We'll get to that later, but yeah.
They'll try and balance themselves out. They'll try to even out just naturally. Your alternator, kind of re-energizes them and re-separates them every time you run the car. But if you just leave the battery there and put a load to it, it'll find balance, and then that's when your battery's dead.
Okay, so explain what's happening on the positive side. Then I know there's there's electrons jumping out of the negative post now.
Yep. So on the positive post, it is electron hungry. The atoms in there are short on electrons. The atoms are positively charged. They're more protons than electrons. So they have a positive charge. They're going to attract anything with a negative charge. So when you attach copper wire that copper wire, has got some free floating electrons. It'll start pulling those electrons through. And if the other end's not attached to anything, you're going to get no flow because you can't get the other end of the copper wire. If you start pulling away electrons from there, it's going to start being like, hey, I want electrons too. It's going to very, very quickly even out, so you don't get any flow until the other end's connected to
How do
something.
you keep the positive balance on that?
Well, like I said, in the battery, it's a chemical reaction occurring inside the battery, always replenishing those until the chemical reaction is depleted.
They put insulation material in between
True.
positive and negative plates.
Yeah. So yeah, you don't have flow going in between between the two posts of electrons.
No, it's just electricity is a mystery. Thank you.
And I think I'll talk about AC later, but if I don't, remind me. Okay. So batteries. So on the either terminal of the battery, you've got a voltage, is what we call it, and voltage is a potential energy, and it's quantized, so it's per how many electrons, but it's a potential energy essentially. So if you have a big difference, side here. So if you have a big difference, a lot of negative and a lot of positive charge, you'll have a high voltage because there's a lot that really wants to cross over. So, kind of blocking it. And as you have less of a difference, you have less voltage. And even if there aren't any protons, you should have a whole lot of electrons. They're still going to repel each other.
Laser pointer.
What's that?
One laser pointer.
Yeah, I should have thought of
I
that.
got it right here. Well, my batteries.
Yeah.
Should have not enough electrons.
Also got a mouse. So
How many batteries are on here?
Maybe.
Batteries?
Button cells?
so
I believe.
even if you don't have even if you have just some neutrally charged atoms, but some negatively charged atoms, you can still get some flow until they even out, and that's going to be a really low voltage. And negative would be the opposite, flowing in the opposite direction. Let's see. So I guess the size of the battery doesn't necessarily determine how much voltage you have. It's just chemically inside the battery, what it's been, the chemical reaction keeps the potential difference between the two of them constant to be. So even though these are totally different size batteries, the chemical reaction inside both of them keeps them both at a difference of 1.5 volts. Just one will last a lot longer. And probably has more of them to be able to transfer over higher current. We'll get to that later. Whenever describing electricity, people always revert to a water analogy. And for basic electronics, that works, and I'll try to throw that in as well. So here, you've got water high up, and for it to fall down, it has a lot of potential energy sitting up there, and the amount of kinetic energy it gains falling from that high place all the way down to the ground, or flowing all the way down, that would be like the voltage difference, the energy levels between the water from a high and low place. It's also described as pressure, because in hydrostatics, the pressure is related to the height. I don't know if I'm muddling this or if I'm making any sense to anyone. If you have any questions or have another way of describing it, go ahead.
Voltage is this setting in the air. Okay. It's not moving, but it has a lot of potential to hit the ground. Okay?
Archery.
The difference from here to the floor, or from here to where it's going, is your difference in positive and negative. That's the easiest way I ever thought of it. Anything sitting in a static state has potential to go, but until it drops, nothing happens. That's voltage. Until you go from the higher state to the lower state, or however you want to describe it, nothing happens in between there until there's a place for it to go.
The higher up you are, the more voltage you have.
And that's the difference. That's how much voltage you have. It's the difference between the two.
So you have potential energy and kinetic energy, and yeah, the kinetic energy, how much energy it gains as it falls that far, is the same as how much potential energy it has just sitting up there. So if you raise it higher up, it's going to have even more potential energy, and in our analogy, more voltage.
So, so somebody has a, in most houses, you got 120 and your dryers and your stoves for 220.
Mhm.
So really what you're saying is that it's because it's,
There's more energy.
There's a bigger difference between negative and positive of 120 or 220 than 120. A larger distance.
okay, dumb question.
So, yeah.
All right. My house, I got a 200 amp service, right? How do they make that distance? How do you go, how do you I got 120, how do you increase it so it goes to 220? What actually do they do?
Well, let's
That-
let's
let's
get to
get
that.
back to talk
Yeah,
about AC.
keep that for later.
Yeah.
But let me kind of explain one other thing here. In this equation, we're talking about gravity and moving something through gravity to gain energy. For an electron, what we're talking about, an electron, moving it from somewhere where it's got a whole bunch of negative charges around it, pushing it away, to somewhere positive where everyone wants it to be. You're talking about a change in charge, how much charge is here and how much charge is there. Voltage is the potential energy is equal to the kinetic energy of moving that electron from one charge level to another charge level. So that's what voltage is. Potential energy is equal to the kinetic energy of moving an electron from one charge level to another charge level.
You think about it in air pressure too.
Yeah,
Because
so
when you put 60 pounds of air pressure in a car tire, it doesn't weigh 60 pounds more. It's just got that potential there. What you've done is you've increased the potential. You're not increasing the weight or the height or anything else. It's just
the potential for it to do work.
yeah.
Else?
Yep. Sorry, yeah, go ahead.
What would you recommend to like negative voltage?
Kind of like in that description there. I mean, like in the real world.
Yeah.
Where do you run to it?
Audio amplifiers a lot.
Yeah.
Yeah.
Or amplifiers in general. I don't know if we're going to get into op amps or not at any point in this, but if you only supply a positive voltage to an op amp, it limits, on just how much it can amplify and how it can amplify it. But if you put a positive on one side and a negative on the other, then it increases the bandwidth. But usually it's in amplifiers.
And in static. What you call static electricity, that's also where you see a high negative with no place for it to go. You have to find a place for it to discharge. That's what lightning is. You're building up a negative charge in the clouds and everything. Until it gets high enough, it's actually a negative charge that just sits there. It's purely negative. There is no positive place for it to go until it gets high enough that it can overcome the insulation.
So I guess kind of the idea here is that it doesn't always flow from positive to negative. You can also get it from flowing from a lot of negative to a little bit less negative. And that would still be an electric flow that is negative. All right. So capacitors are kind of like batteries in that they'll have voltage, but let's see. So first of all, commonly a capacitor is modeled as simply two parallel metal plates. And these plates, if you attach them to a battery, something with a charge difference, you'll get a lot of. If you connect to a battery, the negative one's got a whole lot of electrons pushing against each other. They're going to push off over here and gather up on this plate. And similarly, on the opposite side, it's going to pull electrons from that plate and be positively charged. Now, what happens in a capacitor is that between those two plates, because you've got positive and negative so close to each other, they're going to create a electrostatic field in between the two plates. And that field is then going to counteract the charge between them and thus allow it to pull more charge to either side. And thus a capacitor can charge up and hold quite a bit of charge. And how much charge it can hold up has to do with a couple things. I've got an equation over here. Has to do, first of all, with just the size of your two metal plates. So the area, how big the two plates are. And inversely proportional to the distance. So the closer you get, the more charge, the stronger the field will get. Because if you think about it, the further you move things away, the less the field is, less strongly magnets are held together, and the further apart you pull them. Though that's magnetic, this is electric. You get the idea similar. And then also the permeability of the dielectric, which has to do with how strong of an electrostatic field you can build up in that material between the two plates. So before I go too further, the water analogy, people use a rubber gasket as an example. So you can see there you've got pressure pushing against one side of the gasket. No water is actually going through that gasket, but it's pushing the water on the other side, so you can get a bit of pressure moving through a capacitor, even though you don't have any actual electrons or water moving through the capacitor. All right. Questions so far?
Are you going to get into what you do with all those electrons? Talked about charging, and now what?
Well, yeah. So you have a charge. You build up a charge on the capacitor, and you can either use that, just as a voltage source, very briefly, or later on when we talk about circuits, we'll talk about a lot of uses for capacitors, such as filters and AC, where you have varying voltages. Capacitors really help out in keeping things smooth or calm because they're very fast to react and can provide voltage very quickly, even though it's small amounts. And we'll talk about that in the next couple classes. But also wanted to talk a little bit about kind of like how capacitors are made. So that dielectric in between, just in air, you can kind of get an idea relatively the permittivity in air would be 1. But if you put a ceramic in between there, you can get a lot stronger magnetic fields in there, 12 to 40 times stronger. There are also capacitors. I'm just kind of talk about these two very common ones, ceramic and electrolytic. Electrolytics are not as strong as ceramic, but as you can see here, the top there is a common ceramic capacitor, and it looks very much like our model. It's just a disc with some ceramic in between and then another disc. But as you can see, that you can only get so big with something like that. When you have an electrolytic capacitor, you can have one material with an electrolytic in between, which has a couple properties which make it a lot different than ceramic. First of all, it's thin and flexible, and what that allows you to do then is to put it on a very long strip and roll it up. And so you can get something that's in the same size as a capacitor, a ceramic capacitor, and even though the dielectric is not as strong as ceramic, it has a whole lot more surface area between the two sides of the capacitor, and so it can hold a lot stronger charge. However, electrolytic capacitors, what separates the two panels is can only be charged, can only create an electric field in one direction. And therefore, electrolytic capacitors aren't very good for AC or anything where your voltage could go positive or negative. On an electrolytic capacitor, you can only put positive and negative on one set of terminals. Ceramic, it doesn't matter. You can do it on either side. And then briefly, kind of talk about what to expect when you're charging a capacitor or discharging a capacitor. To start off with, they're neutral, and so it's very easy to add charge to them, and they will quickly charge up. But then it levels off until it reaches a maximum, which is determined by how strong of that electrostatic field you can create between the two sides. And then when you discharge it, it quickly discharges at first, and then it kind of slows out. And how fast all that happens, we'll talk about later when we're talking about building circuits. Yeah.
On your y-axis, what's an RC?
Actually, in this one, it has to do. C would be the capacitance. So capacitance is like how I was saying earlier, is determined by the area, the distance, and what's in between. And capacitance is how much charge it can store. Per volt. If you apply more voltage, it can charge more charge up to a point. You have to check your capacitor because they can only do up to a certain voltage. So that's something else you have to check. And so in this, RC has to do with actually kind of the internal resistance of the capacitor to like how much resistance there is for the charge to move out. So R and C are just actually, I guess that has to do with time.
Yeah, it's basically your resistance to charge.
Right. All right, so next we're going to talk about current, which is the flow rate of charge through a wire. And so in your water analogy, a lot of current would be like a big pipe flowing a lot of water through, whereas a low current, you've got either a smaller pipe or something blocking your flow of water, and thus you have less current flowing through. And similarly here, these both have the same voltage, the same potential energy of the water, but this one has a bigger pipe, this one has a smaller pipe, so this one has more current flowing through it, and this one has less current flowing through it, even though they have the same voltage. And in as far as electrons go, it's kind of the same way. If you've got a small wire or a big wire, a lot more electrons are going to flow through a bigger wire. We have more current, and similarly there, and also has to do with like the impurities in your wire or your material that would block the flow of electrons or inhibit the flow of electrons, and that's what we call resistance. So resistance is the opposition of current flow. And let's see. And so current is measured in amps. And as you can see up there, 1 amp is a coulomb per second. A coulomb is just a measurement of how much charge you have. So that is amount of charge flowing per second. That's what an amp is. If you're curious, like in 1 coulomb, there would be 6 to the 18th power electrons in a coulomb of charge flowing. So a lot of electrons. So resistance is the opposition of flow to current, and in DC circuits, it's often called resistance. In AC circuits, you might run into what's called impedance. It's very similar to resistance, but it's has to do with the resistance of the circuit in whole to resist the flow of current or the change in the flow of current, and a little bit more difficult to calculate. And I'm not really going to go into that.
But on the picture he's got down there,
Yes,
where you
Ohm's
have
law.
higher resistance, no, the higher
Nope.
resistance, and where you see all the material in there, every piece of wire that you buy has a certain resistance per foot. And it's all made of copper, but it's how pure the copper is to how much resistance you have per foot of wire.
Yep.
So this will make a difference when you get into circuits and things
Right.
like that.
Yeah, and I don't know if you ever strung a whole bunch of extension cords together, but that's a bad idea because you just keep, that wire, it carries electricity, but it has a limited diameter and it does have a built-in resistance, and you can only carry so much. And so as it's flowing down all of that wire, it gets hampered and hampered more and more, and you'll get with a lot of that resistance. According to Ohm's law, voltage equals current times resistance, or you can do some simple equations to move it around. But if you've got like a light bulb on the end of your at the end of your long chain of extension cords, the light bulb is going to draw a certain amount of current. But if you're going down a whole bunch of wires, all that resistance is going to add up. You're going to have a voltage drop, and so if you chain a whole bunch of extension cords together, you can get a drop in voltage at the end.
And I think you covered this in a later slide, but resistance basically converts electrical energy to heat.
As well,
So that's why also your long extension cords are gonna
start to heat
get
up
really hot.
and could be a fire danger.
A pointer.
I see. That might work.
Old school.
I'll try not to poke a hole in the screen.
But how can I run a electrical wire from the pole in my house all the way to my house, all through the circuits in my house, and be okay? But if I run extension cords, I'm got too much resistance.
Well, so
Some of it is gauge.
some of it is the size of the wire. So if you have a bigger wire, you'll have less resistance unless you can go further distances with less drain. And if you're putting in electrical in your house, depending on how far away from your electrical box and how many circuits you're going to be putting on it, will determine how big of a wire you need to put in your house between your outlets and the breaker box.
And your house isn't one continuous, cord.
Yeah, it's not all in series, it's just parallel. All right, so wattage, it's a little bit harder to picture because it's a calculated value, but it's how much power, it's how much work is done over a period of time. So it's just like how much current.
I'm sorry, Nelson, if I may.
Yeah.
Would you just back up one more slide? Because you're getting into more, but you haven't defined Ohm's law as to what is what. What does I stand for?
Sorry,
in
I
feet and
have
hour?
it. Yeah, so I in Ohm's law is your current. which up here, current, so that's the flow, is current, I, and it's measured in amps. A lot of technical stuff, a lot of things to remember. V is your voltage and measured in volts. That one's a whole lot easier. It's all a bunch of V's. And R is your resistance, in your material, and that's measured in ohms, named after Ohm. So Ohm's law. Actually, don't know.
The equation.
Yeah.
So can I take away, then the higher the ohms, the more resistance it gets, right?
Right. Go ahead.
In the equation before that one, I didn't get what everything standard for.
Sure. This one, capacitance. All right. Now this equation is kind of simplified for what's that?
There's a lot more to it.
Yeah, there's more to it. That one in particular is the permittivity, and that has to do with the material in between. And whereas these are relative permittivities, you can't just put one in there. There's actually another equation that you have to do to figure out what the actual permittivity is. So that element just has to do with the material in between your two plates. But otherwise, area, the surface area of your two plates, and that's pretty basic. And then D is the distance between your two plates.
Fortunately, we won't have to calculate what the value of a capacitor is because it'll be given to us on the
When you're building your
itself.
when you're building your circuits, the capacitor will tell you what.
But understanding the makeup.
Yeah. Go ahead.
What is Q?
Q is charge. So that would be kind of like how many electrons you have. It has to do with not just electrons. Electrons have charge, and that is the positive and the negative forces repelling each other in electrostatic, like the balloon, that force pushing against each other. So that's how much charge it has. And the bottom one is voltage. All right.
Just want to make sure I've got this
Yeah.
clear. Voltage is the maximum potential you've got. So you can go up to this many volts of electricity, but no higher. That's the maximum you would be able to run out of the system, but you're not running anything yet. But the amps are what's running out through the speed at which the electrons are moving through your system.
Right. Yeah. Current. Is the flow. How many amps is how much charge is moving through your wire, through your system, your circuit. And voltage is just the potential energy. How much pressure there is to push those electrons from one side of the battery to the other.
Okay.
So
Often it's
Voltage
a
is the
combination
potential
of
to do
those.
work. Current is the work being done.
Yeah.
and then power is then work done over a period of time. And so for this equation, joules per second. Joules is a measurement of how much work is being done. So that's work. That's literally work per time, seconds. A joule is the same thing as your voltage times Q, which is once again charge per time. And if you look at those other equations and shift some things around, you get power is equal to the current times the voltage. And you're going to
That's
use
the easy way to think.
Yeah, you're going to use that a lot when designing circuits because how much power, how much work is being done. That work is going to get translated into something else. Either a light bulb is going to make light, or a motor is going to make movement. But resistors will make heat, and so when you're picking a resistor, you're going to want to look at that equation and calculate how much how many watts that resistor is going to be burning up in your circuit, so that you can pick a resistor that is big enough to handle that amount of heat being dissipated. So, next we're going to get into electromagnetism. So far we've been just talking about electrostatics, charge, and how positive and negative charges push against each other, and that's what causes electricity to flow. Now we're going to talk about the other half of the photon and electric fields, and that's the electromagnetic field. So we've got two laws here that we're interested in. So Ørsted's law, a steady electric current creates a magnetic field around it. So here, if you got your right hand and you just take it like that, your thumb is pointing the steady electric current. So electric current moving positive to negative like this is going to create a magnetic field around it. So you're going to create a magnetic field in the direction around the current. So if you've got a wire with current flowing through it, it's going to create a magnetic field that revolves around it. That's not too useful all the time, but if you take that wire and you coil it up a whole lot, then you've got that cross section with electric fields going around it. And now that you've got a whole bunch of them all stacked up next to each other, you can see how those magnetic fields kind of start adding up with each other. Instead of creating just this circular one, you get a big one that kind of goes through the center of your coil. And thus, if you have a coil with current running through it, instead of just having magnetic fields revolving around it like this, you can get additive effect of a magnetic field going through your current. And thus you can usefully get a magnetic field north-south through a coil like that. And the easiest way of thinking about that is just making an electromagnet. You take a nail and you wrap a wire around it a whole bunch of times and connect either side to a battery so that you have current flowing through it. You're going to create a magnetic field going through the nail, and thus you have an electromagnet. And as long as you have current flowing through there, you'll get a magnetic field through that nail. And if the nail is made out of iron, and you do this long enough, the iron molecules will kind of inherently line up and be magnetic itself, even if you're not applying a current.
That's how a lot of magnets are made.
Yeah.
Residual.
So the other law, Faraday's law, is that a changing magnetic field through a coil will then create a voltage through the coil. So that's kind of the opposite of that. And so with those two laws, you can get all sorts of useful applications. Most commonly being motors or generators. They both work very similarly. Here you've got a coil that you're passing electricity through, and what that does, like we said, is it creates a magnetic field through that coil. And so you've got a magnetic field pointing like that. It's going to want to align itself between those two magnets. So it's going to pull that coil until it aligns with those magnets. And in this one, which is a very simple brushed motor, what you have is called that because you have these little brushes here. And if you can see, this wire is connected to this half of a cylinder. And as it turns, that brush is going to then move to this gap, and then it'll just kind of keep turning from its own inertia. Thank you. And then it'll attach. Then it'll be touching the opposite side, and then current will be flowing the other way through that coil, and then the magnetic field will be the opposite way, and so that inertia will keep it spinning a bit until it then wants to start pulling. First of all, it's going to, instead of being attracted to this side, it's not going to be repelled from this side. and it's going to then continue spinning, and that's how you have a brush DC motor.
So the brush is on the wire, not the cylinder.
Right, so you've got your battery here attached to some brushes, some metal brushes that are brushing against this split ring commutator, as it's called, and that is what is spinning, is attached to your coils.
The brush doesn't spin, but it sits there. It spins around it.
Yeah, right, that spins inside of the brush. And the brushes just allow it to move past while keeping electrical contact. Down here, we've got a different type of motor called a stepper motor. This one doesn't have any brushes. It's a little bit harder to use, but it has its own uses as well. You've got the center part that spins, which doesn't have anything connected to it. It's just a bunch of magnets sticking out in set intervals. And then you have a coil, these different coils that you magnetize in series. And so, see, you would magnetize this one next, which would pull that magnet towards it. And then, that one would be slightly further off, and then you magnetize the next one. And so you get it to spin that way. And so like I said, that it's a little bit harder to use one of those, but it's very useful because it happens in steps. So you can do degrees of movement or kind of precisely know exactly how much something is turned because you've told it, exactly how many times for the magnets to switch around. So that's a stepper motor. Any questions about motors? Another common use of electromagnetism is a transformer. So here on one side, you've got current flowing through a wire that goes through, that creates a magnetic field. And this is an iron core, which will hold that magnetic charge and create a magnetic loop here. And then on the other side, you've got another wire with twice as many turns on there. And so this current creates a magnetic field that's the same strength. And then over here, because you've got twice as many loops around it, you'll get twice as strong of a voltage coming out. And come to think of it, this is only AC, right?
Yep.
Yeah. Because
you can't.
Yeah. It doesn't work for direct current because Faraday's law, it has to be a changing magnetic field. So if you have a bunch of coils and you move a magnet through the coils, it'll create a spike of voltage. But if you just put a magnet in the middle of the coils, you get that initial spike, but then you stop moving and you're no longer creating a flow of electrons. So it has to be a changing magnetic field. So that's why it has to be an alternating current. I'll talk about that in a bit. So that's a transformer.
If I may.
Yep.
The interesting thing on the transformer is it actually does both of those laws that you just talked about. The first one is you put voltage through a wire, you induce a magnetic field.
Yep.
The second one, you move a magnetic field through a wire and you get a voltage. So it's using both, which in my mind, it's so obvious, right? If you have a magnetic field and you move a wire through it, you're going to get voltage. If you have a wire and you put voltage through it, you're going to get a magnetic field. But those two different laws were like 10 years apart for them to figure that out. But the transformer uses both of those, which is really pretty cool. And the number of coils that you have, you don't have to have double, right? You can have the same, or you can have less, or you can have more, but you're going to get different amount of voltage depending upon how many coils you have, because the magnetic field is going to be going through each of those wires.
Yeah. All right. So last one I'm going to talk about is called an inductor. We don't use them very often, but they are very similar to capacitors in that they can store energy in a circuit. But like a capacitor will store charge and thus voltage. An inductor stores current. Capacitor creates a electrostatic field that holds the energy. An inductor is like all the other instances we've seen. It's just a wire wrapped around a core. So it's creating a magnetic field in here. And an inductor, if you then stop supplying current, that magnetic field is still going to be there, and it's going to dissipate and create current then in the coil. And thus, it's a way of storing current in a circuit.
Again, both laws just on the same device.
On the same device,
through
different times.
Yeah.
Over time, it can be either charged or discharged. And an inductor, similar to a capacitor, it's defined by at N, the number of how many coils, how many turns there are, the material that you've got in the center of the core, the cross-sectional area, how big your coils are, and L, the length. I think that's the length of the wire.
Dumb question here. When I was a kid, you used to have train sets, okay?
Yeah.
You always had to hook up your transformer and your track. And it wasn't delivering 120 volts to the trains, obviously, right? You got over there, primary, I'd say it's 120 volts coming in, and then you need, what, 9 volts coming out? I mean,
If you flip it around and send the electricity into the wire that's wrapped a bunch of times and have it coming out of the one that's wrapped fewer times,
yeah,
it'll go down.
okay.
So if you're coming in at 120 with twice as many
Okay.
wraps, if you want 9 out, you go
And
with
to make it,
fewer ones.
Okay.
to make it real easy, let's just say you have 120 wraps on the wall side, you need 9 on the output.
Okay.
So you
You're
have
9
20
volts.
volts on one side and then 9 volts on the other.
Right. Got a dumb question then. If you're gonna explain it later, okay? I'll shut up. What's an inverter?
It's
DC to AC is typically what you would
Yeah.
convert an electric, a type of electricity. You're right, converting DC to, or AC to DC, and you invert DC to AC.
Yeah, you rectify AC to DC, and then you invert DC to AC.
Yeah.
But it's
We
basically,
can probably go into it more later, but
Let's go into it.
can you picture, I mean,
When we start talking about AC, you'll understand.
Yeah.
You'll
All right.
understand it a lot better.
Yeah.
you almost gotta see it.
Yeah.
I'm not sticking my finger in the light socket. I've done that too many times. Thank you.
I don't really, I don't think I really talk about AC too much, except in this slide, which is very kind of a biased slide. But, right. So, these two people, everyone knows Edison, and now a lot more people know Tesla. He's kind of getting a lot more recognition lately. But they were pioneers in the early day, and Edison was all for direct current. Tesla was for alternating current. So in direct current, you've got a positive and a negative charge, and you have like current flowing through in one direction. You just always have electrons moving through there. And in alternating current, instead, you have a wire where you are not just pushing, there's not actually a net flow of electrons through the wire, but instead, it's kind of like that capacitor analogy with water and the diaphragm. You've got the charge changing. So you've got a force pushing charges this way for let's say a few seconds, and then it stops pushing them away and then starts pulling them back. And so that's what alternating current is it's pushing and pulling, and that can travel down a wire just as well as DC. Well, better than DC, and I guess that's kind of the difference. In
Question, I think.
yeah, go ahead.
I feel like use like DC around like water a lot for some of them travel through water. Like submarines and something that like use DC instead of AC. Water.
No.
Okay. I wasn't sure about that.
So
Water conducts electricity the same,
Okay.
which is actually, water is a very, very poor conductor. It's the other stuff in the water that conducts electricity.
You actually would have more of a buildup with DC, I think, because of the solid charge on, stuff that is touching the water. You get, really on the boat motors are anodes, I guess is what they do.
Well,
They have zinc, just waste metal.
Right.
But the different, anytime you have a potential difference and a different material, you'll get some reactions.
yeah, we're getting into corrosion and stuff there.
Yeah, but AC, you alternate those charge differences, so I think it might be even less impactful than DC.
No, it still has to do with the resistance of the
So it's just the
material.
potential is there, so it would be the same.
So if you've got a wire with a positive voltage, then you'd say that it is, over time, the voltage in a battery, as you're dissipating it over a short time, stays the same. It's that chemical reaction is always going to provide that same potential energy of, let's say, 5 volts in your circuit. So it's always going to be providing 5 volts of current in your circuit over a period of time. Alternating current, however, as a power source, over time, it's pushing electrons, so at 5 volts. But then over time, it then is pulling electrons at -5 volts, and then +5 and negative, and +5, negative. So over time, that is what alternating current looks like. And perhaps that helps you visualize the difference.
If you draw the line going back to negative, put arrows on it, you can see the difference a little better. That way you can see that the flow is always one direction with DC.
What do you mean?
Basically, your electrons are always flowing from a negative source, okay, around to a positive source, okay? Now, what you're doing with AC, okay, is you're constantly switching those two, okay? So the electron jumps and comes back, and does all the work it needs to do in this much space instead of this much space. That's what makes AC work 100 times better than DC is it does it in this much time frame. It does all the work in that much time frame, whereas with DC, it would take twice, 3 times, depending on your frequency, how long.
Now, the trick is figuring out why UE needs to keep charging you if they just keep pushing and pulling those same electrons back.
They're charging you for pushing and pulling.
So why
Get used, but
why is it that electricity travels better over far distance on alternating than direct current?
Because the electrons are only traveling that far.
Right. Okay. Yeah.
See, what you're doing is you're doing the work and coming back in a little tiny distance. So there's less heat created.
Oh, plus they jack the electricity way up for high power.
The higher the voltage, the
Less current.
less current. Yeah, that's
Less
in
the less
terms
power.
ratio.
Yeah, so less
Power
cable
gets wasted.
size,
Yeah.
less everything.
Something I never mentioned that I was also found interesting is that we're talking about we're saying electrons are moving, but what's really conveying the force is the charge pushing the electrons. And that force is, as we said, transferred by the photon, which, like the electron, is massless. And like all elementary particles, travels at the speed of light. And so thus electricity, if you're in a perfect conductor with absolutely no resistance, nothing blocking its flow, electricity moves at the speed of light.
So let's get together later and see if we can create that, because we'd be millionaires about this.
The perfect conductor. Yeah. Superconductors. That's a big field right now, trying to get a room temperature.
Room temperature, that's what I was gonna say, do it, then room temperature.
Yeah, we could do it at,
Yeah,
what is it,
zero.
300 degree Kelvin?
Yeah.
Keep your drink cold.
Yeah.
All right. So I'm going to try and talk a little bit now about semiconductors. And in semiconductors, our previous examples of talking about electrons as particles moving kind of breaks down, because electrons, like all elementary particles, wouldn't be described as how we see the universe as a particle. Down there at that macroscopic level, there's something else. We can describe it sometimes like a particle, sometimes we describe it like a wave, like just a wave of energy. So when we're talking about semiconductors, it's a little bit difficult to describe it just as an electron moving. So I'm not going to get into, I don't fully understand, so I can't fully describe what exactly is happening. But we're going to talk a little bit about how they're made and what they are. So a semiconductor is something in between a perfect conductor or a good conductor like copper and an insulator, like plastic. So a semiconductor is somewhere in between. And silicon and germanium are both commonly used semiconductors because they create these crystal structures that you can embed other elements into, what's called doping the elements, doping with another type of element. So depending on what kind of element in there, you can create two different types of semiconductor. If you put in an element with an extra electron, you'll have an N-type semiconductor, something with extra negative electrons in it. It has donor free electrons. Whereas a P-type, is you're putting in an element that would be short an electron and is then, positively charged, a P-type semiconductor. So you've got these two different types of materials that are used in computers primarily, but in diodes is the simplest way of putting them together. You just N-type and a P-type semiconductor. So the P-type, if you attach to the positive end of a battery, and the N-type to the negative end, you can then get you'll then get flow through it, but only in that direction. Let's see.
Yep. So they're good for blocking electricity going the other direction.
Yeah.
They stop it. They only allow it to go from the anode to the cathode, and not positive from the cathode.
Yeah. Cathode, anode.
It's like a one-way street.
Yeah. So it's a one-way street. And so the N-type only has an abundance of, already has, some electrons embedded in it. And so when you apply electrons to it, you can kind of get electrons thus flowing through that material. Whereas if you were to apply, negative electrons to the P-type, which just has holes, you're not going to get that movement through it. It's just going to be like, I'm different than you, and you don't get any flow through it. That's a simple way of describing it. And then the next, probably most common use of semiconductors is the transistor. And in a transistor, you can set it up either with 2 negatives and a positive, or 2 positives and a negative. But a transistor kind of acts like a switch. So you have base, collector, and emitter. If you apply a little bit of current between your base and your emitter, that will then allow current to flow from your collector all the way through. So it's kind of like a switch in that if you say, turn this one on, then this one will turn on as well. And no, I don't. I guess I don't really get into it any more than that, but but so you can't get any flow, from this end to that end until you saturate the base, the middle one. Yeah, so you'll use these a lot in circuits and digital circuits, and just kind of remember. Yeah, what's that?
Analog too?
Yeah, analog too. Yeah, amplifiers and such. So.
The best part about that is basically what you apply on B adds to your C so that you get all of it out of E on the NPN there. And conversely, on the other side, the 2 C and E add together with B, and you get more out of the output than you do with just having a switch. All your energy goes through there and creates a higher signal or anything on the other end.
Yeah, so this is all solid state. We're just talking about electrons flowing. There are no actual parts moving. Before this, we had to have relays and vacuum tubes, and they're big and expensive, and they're moving parts, so they're always breaking, causing heat. And yeah, it wasn't until you got semiconductors that you could start making things reliably and small and
Not also a room heater.
What's that?
Also not a room heater.
Right, yeah.
Yeah, well, ENIAC was as big as this room and didn't have as much.
Computing power less than a phone.
Yeah. Than a digital watch.
You're also loud. Which is why when you get that old-fashioned computer sound, there's actually a loud hum or even clicking. If you slow it down enough, it's actually clicking.
All right. So I'm going to play this clip. I think it's about 5 minutes. But I love this guy. He's an electrical engineer. And it's hilarious. He likes to teach people by showing them how to do it wrong.
Yeah, don't do this.
But yeah.
Oh, we're not going to do this.
You gotta wait till you go home.
I want my money back.
Yeah, full refunds.
You can fill out a awesome grant request for it.
I was supposed to go to just the right time.
Oh, no. All good. No, I didn't know.
It's on the left on YouTube, but I don't know where it is.
Don't look directly. Ouch!
So,
well,
at the end of this, he gives a good explanation.
These things get hot. This is not a proper way to hold the electrode, apparently. Do further as possible. Why did I buy these things?
Sorry.
Was enough? If this is 2 volts.
I had it set to start at just the right time, and just the time was.
Ouch!
That's always worth rewatching.
The 2 batteries
This is hot. I can't hold it anymore. 2 batteries is enough to weld, and the reason is the higher volt.
If you go on YouTube and go out to YouTube to do it. Might open another one.
This guy actually has some really good videos. And he's funny. He likes to electrocute himself for the pleasure of others.
What's his name?
Medi
Electro.
yeah.
I would imagine funny guy that electrocutes himself would
Yeah.
actually probably find them.
Oh, there it is.
He has some really, actually, some pretty good, both explanations of stuff and,
Have to get to the end first.
It's great. Now I'm hungry. Oh.
I don't have ad blocker on this computer.
That doesn't do anything.
Not what you did.
It does.
it does the side stuff.
I'm using the right ad blocker. Okay, so he's got right now he's got 10 car batteries all chained together. So 10 12-volt DC batteries. Put them all in a chain, that adds up, and you have 120 volts DC. And so right now he's just showing he's got a regular light bulb.
So this is 150 watts. What I'm trying to do is that I'm going to connect that somehow to that battery, and I'm gonna turn it on. How do I do that? Now, don't short your batteries. How many times do I have to tell you? Doesn't matter. I'll get through this, don't worry. I'll just take this out. Okay. Okay. Ready? Let's see if the bulb turns on. See? 120 volts. It's electronics, it's not me. So it's effectively exactly the same voltage as the 120 volt power plug. Like, over the same resistance, it provides the same power. Now, do you think I should touch this? Finally, some answer. Well, I'm going to touch it. So, oh, it actually has something. I felt it. It's not too bad. Well, I expected it to just kill me, but it didn't, which is good. It's always a positive. Yeah, I can feel it a little bit. Nice. Not awful. But the thing is that if this was AC voltage, it would just kill me, right? Okay. Never mess with AC. You can't mess with DC a little bit. But actually, is it possible that I degraded the battery when I shorted first time? Nope, it's good. Okay. So there you go. It's not hurting. It's a DC voltage at 120 volts, which is the same power output as the AC, but it doesn't hurt. Can it weld? Should I try that? Fine, anything for you. Ready? If you want to move out of the room, this is your chance. Ouch! Zapped me. So it still hurts. So never try this at home. Okay? Ready? Don't look at it directly. Wow. Should I try it again? It was too fun. I want to try it. Don't look directly. Beautiful. I've never done that before. Good thing I'm alive. Look at that, it's all red and beautiful. So it can weld, but it might be too much power. Okay, now conclusion. Well, first welding. To weld, being able to provide much current is not enough. You need enough voltage too to create an arc. And the arc is the resistance you need to have enough voltage. So voltage times current equals to power. And that creates heat that does the melting for you. 2 batteries is okay for welding. It's a little bit hard. The arc can't get too large, but 2 and more you can weld. AC versus DC. AC hurts much more. That's what I learned from the people who are leaving comment on my videos. 120 volts is hardly felt, or again, it depends on the skin condition and when, like different parts of body can have different resistances, so you can feel it more if you put it on different spots. And the AC hurts more, and the reason is because of the capacitive property of the body. The body is not only a resistance, it's also a capacitor, and the capacitor, what it does is that it blocks DC, but it allows AC to go through, right? So when there is an AC signal, there is much more current going through, and that will hurt. Current versus voltage. Well, a lot of people say that it's the current that kills, but the fact is that you cannot have current without voltage, right? Yes, it's the current that goes through your body and makes the damage. The voltage is the energy that is needed to move the electrons, right? So the voltage creates the current. Let's say they work hand in hand. That's why you see signs, danger, high voltage. You don't see danger, high current. Like if there is 1,000 amps of current running through one cable, you touch it, you don't get hurt because the voltage might be 1 volt, and that's not enough to create enough current through your body. And if the high voltage is across your body, it can't be limited. Some people say that, hey, the voltage may be 10,000 volts, but if it's limited to 1 microamp, it doesn't hurt you. That doesn't even make sense. Your body has a certain resistance with some certain voltage. You will have some certain current. And the electrostatic discharge, like when you touch your doorknob, there can be 100, like 10 kilovolts, 20 kilovolts, and those sparks are very high voltage. And people say, hey, yes, it doesn't kill you because the current is limited. That's not true. The current is not limited. The current is actually a lot. It might be 100 milliamps. That's enough to kill a person, but it doesn't hurt because the pulse time is limited. It's like 1 microsecond or smaller. So you need that time, the extra time to hurt. It will hurt if it's longer. Some people say, hey, birds sit on like wires that can be 100 kilovolts and they don't get hurt. The reason for that is that the circuit is open, so there's no current going through it. The entire voltage on the body of the bird is equal to the wire it's sitting on, and the voltage across the body of the bird is actually 0. But if it actually spread its leg across two wires, it will be vaporized easily. And that's my unibrow. That was my presentation.
All right. So yeah, electrical safety. Starting out with robotics, you're going to be mostly dealing with DC voltages, probably maybe up to 12 volts. And so while I kind of like the point of that is that he had up to 120 volts, touching it between 2 hands, and he was okay. So you can deal with batteries and you're going to be mostly safe. You want to be careful, but DC voltage, like a 9-volt battery, you'll feel it on your tongue because your tongue is very wet and it's very close together and you have very little resistance, and therefore you'll get some current through your tongue, you'll feel that. But just touching it with your dry fingers, you're not going to get any current because you have a high resistance in your body that's going to impede that flow of electricity. So for low voltages, you can be pretty safe. And the other thing I want to talk about, however, when dealing with Arduinos and digital circuits like that, is to keep in mind electrostatic discharge. Because if you're wearing a big sweater, you can, like with the balloon, you're rubbing against stuff, you can build up a big charge on yourself. You can act like a capacitor yourself and build up a big charge. And if you were to touch something that's really sensitive, like a microchip, you can get that voltage that will transfer to you very quickly, and it can possibly burn out your chip. So you want to be careful not to wear sweaters, and if you're dealing with sensitive electronics, you can either wear something to ground you, or you can just every once in a while touch something metal just to make sure, just to discharge yourself.
So you might want to mention the electrostatic bags at this point.
And the difference.
The bags that they come shipped in.
Oh,
They don't.
like
They
that
don't protect you against the.
This is an anti-static bag, but you can still zap the chip right through this. It's not static shielding. It just, you can rub it together all you want. You can rub it on your hair, rub it on the fabric, rub it on a balloon. It will not create static, but you can still zap the chip right through. This, the kind of metal looking ones, is actually a shielding bag. You cannot zap the chips through this. So there is a big difference.
Because that second bag is actually conductive material.
Right.
The charge goes around the item.
And sometimes you'll notice your chips come on this black foam. This foam is actually conductive, so it's the same as the bag. As long as it's on the foam, it's, well, I'm not going to say completely safe, but it's reasonably safe from static. But again,
Yeah,
these blue ones or pink ones will not create static, but you can still zap the crap out of electronics that are in them.
A lot of people think that the bag doesn't conduct because it protects, but actually it's the opposite. It conducts, so it allows the current voltage to discharge around it, which is actually a question on the A+ exam if they would take that.
These guys are nuts. Both of them.
Yeah.
Geniuses, but nuts.
I think those go hand in hand.
Who was the one that did Thomas Edison actually electrocute an elephant to show?
Yeah, it says up
Yeah.
there.
Yeah, it's
Actually
Friday.
more than just an elephant.
That's kind
Oh,
of.
it was a dogs. He would hire people to go and find stray
But-
dogs.
Yeah, but
That's eventually what.
He was trying to show how dangerous AC current was.
Yeah.
yeah,
So
you actually cut off
yeah,
the bottom.
I cut off a lot of where it talks about that. But yeah, so
But yeah,
Tesla, was a proponent for AC because it can go. His generators created AC very well, and you can go long distances with AC without the loss. Whereas Edison was pushing direct current. He thought it was safer, and his argument was that it was safer, and that
One of them
Tesla
was also
more dangerous.
One of them was also for wirelessly transmitting the current to the houses.
Tesla.
yeah, Tesla
And-
was huge on
And
that.
He
Edison,
was trying to make the earth a conductor.
right, Edison was against it.
Yep.
I don't know if you'll be able to answer this, but do you know why they allowed Edison to get elephants and stray dogs to zap them?
It was the 1800s.
That's the short version.
Yeah.
Good,
Different
yeah.
time.
Aeropresto, PETA.
Yeah,
Yeah.
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 Not to say people didn't object, but after the fact. they did.
The funny part about it is the electric chair we kill people with is credited to Edison because of what he did with elephants and things like that.
So we did deal with AC.
I want to know, what do you do with the elephant after you electrocute it?
You did.
Bring it down.
And then you back in the move 3 times.
He attracted the dogs with it.
Edison did the electric chair to try to put Tesla on.
All right. Well, that's about it for the presentation. So.
So what are we gonna
any
go into next
questions?
time?
So next time we're going to start talking about building circuits, and with some hands-on stuff afterwards. So this was a lot of theory and try to get you introduced to a lot of subjects. If there's still anything that was glossed over, you're not really sure what it is, go ahead and use this time now to talk to other people or ask a question. Or, yeah.
I have a question.
Yeah.
So in school, I didn't really learn a whole lot about DC. We learned all the theory of DC and voltage division and all that good stuff. Arguing about AC. Do these equations apply to AC?
Yes.
The exact same way they do to DC.
I think so. I
The
think
ones
I'm
he
the same
showed
way you are.
Okay, yeah.
you showed, the V, the I, and the R.
Yeah.
Okay.
But in those cases, would you be talking about like the, I
How
guess,
you determine V.
how you determine the V? Yeah.
Yeah. It's how you determine the V, and
Because it's always changing over time, so then you're talking about.
AC voltage. When you measure AC voltage, what you're measuring, okay, is 80% from here to here. Is this difference is your voltage.
Well,
Okay.
that's what we call, yeah, when you say 120.
When you say
volts,
120 volts, it's that distance right there. Okay, it's 80% of it. So actually, the total percentage of it might be 150 to 160 volts. But what you measure is 80% of it. Okay, that's why you do a lot more work with this than you do with this, because you have to be way up here for 120 volts of DC.
Gotcha.
You're not measuring the distance from here to here. You're measuring the distance from 0 to here. Whereas at 120 volts, you're measuring it from down here to up here.
Voltage rise over time is
Yeah.
much more.
Even though you're using,
I
you have
explained that
150
wrong. I
volts
was
really
wrong.
peak to peak.
I was
For
wrong.
the- For the formulas, if you're using what he's showing as the RMS, if you use the RMS value, then those formulas are.
Okay.
I'm sorry, I described that wrong. It's the distance from here to 80% of the top of the peak, from 0. Mhm. What he was asking about on the 220 volts, okay, they're using from 80% here to 80% here, okay? You're using this whole curve, that's 240 volts.
You
Okay.
split phase.
Yeah. They're using both sides of the phase instead of just from 0, which is your neutral, okay, to your voltage peak or 80% of it.
So then how
So
about
what,
three
what,
phase?
so what
This-
does,
this
what does
distance here.
120 volts AC look like then, coming out of your wall socket?
Right here.
It's only the
It's
top
from-
half,
It's yes.
so the bottom half is.
But it's-
isn't there at all.
It is there. It is there, but it's what you're showing, what you've got. This here is the positive half, say.
Yeah.
This is your negative half. On your way down. Okay, you're only using from neutral to here.
Right.
Okay, so as it rises from here, it's positive to negative. That's what you would do in 120. This over here, okay, would be your other half of that. And when you use both of those together, you're using all of that. I've probably confused everybody.
No, you actually
You
just
have
here's
all
the
your
lump.
reads, just
Something I was gonna
like
ask
that.
about that.
Yeah,
It's
that's
two
the
separate
phase.
Yeah.
But is it still the same?
It's still considered single phase in your house because you're using half.
It's different. I mean, that would still, yes, be for one of those phases.
Right.
When you're using all three in like a three-phase motor or something.
Yeah, that's,
But it's the same. You're measuring the same
Yes.
blade, same percentage.
You just have more power available to you because you have, yeah, you've got more of the time you get usable juice.
Makes sense.
To answer your question, we'll kind of talk about it later, but to give you a visual explanation, if you're rectifying AC, what you're going to be doing is using the diodes in the circuit we'll talk about next week to basically make the waveform to invert, to rectify half of it so that it instead of going down, it's up again. And thus you've got something pulsing like that. And then if you use some capacitors you can then smooth it out a bit. And thus you've got something that, with more capacitors and some more cleaning up looks like a DC voltage. So that's how you rectify AC into DC. And then I'm not actually sure if the circuit's used, but then an inverter then takes it the other way around.
Because
I have friends, you know, I went and helped install inverters on their trucks so they can use their AC tools.
Yeah, a lot of those, the cheaper ones particularly, it's what's called a modified sine wave.
Yeah.
And it's not truly giving you AC, it's giving you more of a pulse DC. But certain AC stuff, they don't mind that, it's fine. The full wave,
True sine.
inverters, are more expensive.
Yeah, the true sine ones are like probably 20 times more.
Yeah.
Like you'll find like a $19 one that'll fit your cup holder and power, you know, small things. But to get one of the true ones, they're probably starting at $1,200.
But for a lot of things, that's perfectly fine.
That's actually better. Yeah. You're right.
What is that called?
That is a
Full
rectifier.
wave rectifier.
Bridge
Yeah.
Bridge rectifier.
So how is that different from Keystone Bridge? Sorry, I didn't get helped out here.
It's a Wheatstone Bridge, I
I'm not
forget.
sure. I've heard that.
It sounds familiar, but I forget.
Yeah, that's what.
It might be the same thing.
Alright.
I just don't remember the terminology. But yeah, we'll talk about that next week. Or the week after, I'm not sure how.
But basically,
This class went longer than I thought it would, actually.
the rectifier just blocks half of the AC signal.
Right. So if you got just a single diode, it only lets voltage through one way. So it's only going to be letting the top half of your sine wave through.
I don't have anything on the theory on it, but a Wheatstone Bridge is resistors instead of diodes.
Yeah,
Okay.
is an electrical circuit used to measure an unknown electrical resistance by balancing two legs of a bridge circuit. Yeah, after we got more on that, we can do- but yeah, it's the same format. It looks the same, but it's using resistors.
All right, let me go ahead and stop this.